Hello, welcome students. So as you know, in the previous class we talked about the harmonic oscillator and we derived the expression for displacement of an harmonic oscillator with respect to time. Thereafter we calculated the expression for energy of a harmonic oscillator. We calculated both kinetic energy and potential energy of an harmonic oscillator. So that was actually instantaneous kinetic energy and potential energy. Instantaneous means time dependent potential and kinetic energy. Okay, but when we did that, we got the expression for kinetic and potential in terms of x, or you can say in terms of time. Okay, so time dependent value we got. So that kinetic and potential you can write either as u of t or k of t, where k indicates kinetic and u indicates potential. But problem is that this expression do not give us much physical significance. Okay, because that is instantaneous. We get a physically meaningful expression when we get something called average value. Okay, because instantaneous value does not have any meaning, and mainly because that is not a measurable thing. Measurable is something which when we take the average, that is only measurable. So today in this class, what we will do, we will find the average value of potential energy and kinetic energy of a harmonic oscillator in a complete period. Okay, because why do we take complete period? In a complete period, you know, the oscillator complete one cycle. So then we will take a time average. Okay, because in different time instant, the value of kinetic and potential are different. You can see from the graph. When you take the average of that, you get a physically meaningful value, and that is of course measurable also. Okay, this has many other physical consequences in different other branches like electromagnetic wave, or say when we talk about alternating electric current, where similar ideas will come. Okay, so there is so that means it has much further scope in the later study of physics. So let us try to understand what is the meaning of average value. Okay, for that we will first look into average value of potential energy. How we will find it? Because the potential energy we have calculated last time, expression was u of t, and now what we will do, we will calculate the potential energy, total potential energy obtained by an oscillator in a complete period. That is what is called capital T. So what we will do, we will integrate the instantaneous value, that is u of t, with the dt. Okay, so then we will get the total potential energy gained by the oscillator, integral 0 to t u dt. Okay, so we will get the total energy. So in order to find the average of this, what we will do, we will divide this total energy with one period, that is capital T. So what we will write then, this is the total energy, total potential energy obtained by the oscillator in a complete cycle. You divide into the total. So you will get the energy processed per unit time. Understand? So you will get the average value of potential energy maintained by the oscillator. So again we can proceed. How we will find the average value? So for finding average value, what we did, we divided the total energy, total potential energy with the total period or complete period. But T is the period of oscillation. And we know capital U is equal to half kx square. Yeah, half kx square. Okay, so U is replaced with half kx square. Okay, So K is a constant. You can take outside. 1 by 2 is a constant. So taking all these outside, we get K by 2t integral 0 to t x square dt. Okay. And x we have already derived last class. X is equal to a sine omega 0 t plus 5. So you can substitute instead of x this given expression. So what we get K by 2t integral a sine omega 0 t plus 5 whole square. Okay, you substituted for small x. That is the instantaneous displacement. Okay, that is a sinusoidal function. Okay, so what you can do, you can keep outside all the constants. So inside you have now sine square omega 0 t plus 5. Okay, so that can, sine square omega t plus 5 can be written in a summation form. Sine square theta is equal to 1 minus cos 2 theta by 2. Okay, sine square theta is equal to 1 minus cos 2 theta by 2. So that is that formula, standard formula is used here. We replace the sine square omega 0 t plus 5 by 1 minus cos 2 omega 0 t plus 5 by 2. Okay, so very simple. Then only we can integrate it. So that's why we have used this standard formula. Okay, where again you can see, you can split up this term. First term will be dt. You have to multiply 1 with dt. So you have the first term dt minus second term will be cos 2 omega 0 t plus 5 dt. This 2 can be taken outside. So outside you have a constant now k square by 4t. So now integration is simple, straightforward. You integrate dt and you have to integrate in the second term. You have to integrate cos 2 omega 0 t plus 5. Okay, that is very straightforward. You have dt, integral dt is t, and integral cos 2 omega 0 t plus 5 will be sine 2 omega 0 t plus 5 divided by 2 minus 1. So your limits are 0 to t. So one thing is clear, when we integrate a sine function over a complete cycle, its value will be 0. Okay, so this is obvious from this expression that only the first term will remain, second term will get cancelled because of this mathematical identity. Okay, integral of any sinusoidal or cosinusoidal function over a complete period or 0 to pi will be giving you 0. So what happens? We have only the first term remaining, that is k square by 40, and you can apply the limits on the small t 0 to t. That will give you capital T. Okay, so T cancel. So what is left is average value of potential energy of the oscillator is k square by 4. Okay, and k you already know, that is m omega 0 square. We have already derived it. We can replace it. So we have now m omega 0 square s square by 4. So this is the expression for the average potential energy of the oscillator. That is the average potential energy retained or maintained. Okay, this may vary. Sometimes potential energy may become 0, sometimes may become maximum, but this will be the average value. Okay, you take the average of value, this will be 1 by 4 m omega 0 square s square. And of course, the total energy of a harmonic oscillator is half m omega 0 square s square. So this obviously is 1 half of that. So you can write average potential energy is equal to E total by 2. Okay, half of the total energy. So we have a conclusion now. The average potential energy is equal to half of the total energy of the oscillator. It is it's not kinetic, it is potential here. Okay, keep in mind. And the same way, you can also find the average value of kinetic energy, because in the energy graph, potential energy graph, potential energy increases when at the mean position or the equilibrium position, and potential energy goes to 0 at the extreme position. So it is obvious that kinetic energy varies at every instant. Kinetic energy varies in every instant. So it is very important to find an average of this. Okay. For an oscillator, every instant its kinetic energy varies. So finding its average over a complete cycle is very important. So let us see how that is done. So how mathematically that is done. First what we will do, we will find the total kinetic energy possessed by the oscillator, because every instant it is changing. So we add up every instantaneous value we add up. Adding up is done by the process of integration. So that is by k dt, where k is the instantaneous potential energy. Understand? So every instant in k of t is the multiply with dt, take the complete period. That means 0 to t. Okay, so proceed. Then what we'll do, in order to find the average value, we will divide the total potential, total kinetic energy with the total time t. Okay, and kinetic energy obviously is half mv square. So we have to find out here, because you know x. What is x? X is a sin omega 0 t phi. So by simple differentiation of x with respect to time, you can get velocity, that is a omega 0 cos omega 0 t plus phi. It is obtained by mere differentiation of x. Okay, now we can substitute for velocity. So on substitution of velocity in this expression, what we get is 1 by 2t you can take outside, and some constants are the mass omega 0 a square. These all terms can be kept outside, and within the integral we have integral cos square omega 0 t plus phi. And obviously we know cos square function can be written as 1 plus cos 2 theta. Okay, so we replace here cos square with, only then we can integrate. That is why we are splitting up. So 1 plus cos 2 omega 0 t plus phi by 2 dt. Okay, rest of the things are already there. This is kept outside the bracket, and you can integrate separately. When you integrate separately, first one will be integral dt, that will give you small t, and the second function is integral cos 2 omega 0 t plus phi, that will give you sin 2 omega 0 t plus phi by 2 omega 0, and the limits are 0 to t. Okay, so what we do when we do that, you know, only first term will exist, second term will obviously get 0 because of the obvious mathematical reason already mentioned. So you have a t here. The net result is that this bracketed term will simply give you a capital T here. Okay, t cancel, so you get the average value of kinetic energy, that is again 1 by 4 m omega 0 square square. Okay, which is identical to potential energy expression. Previously we had a potential energy, average potential energy of the oscillator was 1 by 4 m omega 0 square square, and average kinetic energy now is 1 by 4 m omega 0 square a square. And the total energy we found that is 1 by 2 omega 0 square square. Okay, by adding these two, u and k, you will get this. Okay, so what is the conclusion? Conclusion is that average value of kinetic or potential is independent of time. You can't see any time function. That is a constant, isn't it? That is a constant. It is independent of time. It is independent of x. It is purely a constant, because a is a constant, omega 0 is a constant, and m is the mass of the oscillator. Okay, so we got the expression for average potential energy and average kinetic energy, and its sum average, the total energy. Okay, that is of m omega 0 square square, and it is a independent of time. Okay, so here is the assignment, simple assignment given here. When the displacement is 1/2 of the amplitude, what fraction of the total energy is kinetic and what fraction is potential in a SHM? That's a question. Okay, very simple. We have a standard expression for potential and kinetic, and total energy is given here. And what is asked is what fraction of the total energy is kinetic. what fraction is potential. So in order to get the fractional value, what we have to do, you divide the potential expression with the total energy expression. And here it is as that when x is equal to half amplitude. So you have to substitute with x equal to a by 2. So you will get a fractional value of potential. Similarly, fractional value of kinetic can be also found. Kinetic expression given here. You have to divide like this. You will get the fractional value of kinetic, where x you replace with a by 2. So obviously you will get a fractional value of both the kinetic and the potential expression. And the second question is, a simple harmonic oscillator of period 5 seconds, okay, capital T is 5 seconds, and amplitude root 2 meter has total energy 1 joule. Okay, total energy of the oscillator is given. Okay, so the question is, what is the mass of the oscillator? Okay, with already given expressions, already derived standard equations, you can definitely make out value of mass. Okay, and this is a sub question to this: how much time does it take to reach halfway through the amplitude? Okay, the question asking you, suppose it is starting from equilibrium value, that is x is equal to 0, how much time it will take to reach the amplitude a by 2. Okay, that is you have to find the time taken to travel, say x is equal to a by 2. We have the expression for x, sinusoidal expression already there. You put the value of x is equal to a by 2 and solve the equation, you will get the value of t, time t. Okay, so if you are starting from the mean portion, you can take phi is equal to 0, no problem. Phi is taken as 0, then do it. Okay, so these are the two assignments, very interesting assignment. You can do it nicely and substituting properly and do it beautifully, and I hope you can upload or you can submit in Google Classroom. Okay, hope you enjoyed the session. Thank you all of you.